some practice. Okay? So we've been talking about matrix operations. So we talked about addition and subtraction. So in order to add or subtract two matrices, they must have equal dimensions. And then we just add or subtract the corresponding elements. We probably don't need to do an example of this, right? Next one we talked about was scalar multiplication. So this can always be done. And here we just multiply each element in the matrix by that scalar. Remember, the scalar is just a real number, right? Come on in. Yep. That's you, Ava. Okay. And again, we probably don't need to see an example of this one, right? And we've talked about matrix multiplication. And to make it easier, I'm going to say when we talk about this, we're just doing A times B. So in order to do matrix multiplication, the number of columns in the first matrix has to equal the number of rows in the matrix. And then we take the to calculate an element in A times B, we take the sum of the product of the corresponding elements in the given row from A with the given column in B. Now that's pretty wordy, but we've gone through how to do this by hand a couple of times, and it's a pretty visual thing. Like once you've done it a couple of times, the process is fairly easy to remember to do, but it's hard to explain kind of what it is you're doing, right? If you tried to explain the direction to somebody, they're like, what? But when you show it to them, it's like, oh, I get it. Same kind of thing here. So that's kind of wordy, but it is what it is. We talked about inverse matrices. So the symbol we used there was A inverse. So for a matrix to be invertible, they have to be a square matrix, and the determinant can't be 0. And then yesterday we had developed this formula for the inverse of a 2x2 matrix. That's as much as I'd ever ask you to do by hand in this class. Anything bigger than that, we'll use the calculator to handle, and we'll talk about how to do that a little bit later. And then the last matrix operation that we'll talk about is the determinant. So the symbol we use for that is we put the vertical bars around the matrix A, or you write det of matrix A. Either of those notations are pretty common. The vertical bars around the matrix is probably the more common of the two notations, but they're both okay. So the determinant must be a square matrix. You can't take the determinant of something that's not a square matrix. For a 2x2, we calculate the determinant by doing AD minus BC. So you might notice that that is the product of the main diagonal minus the product of the other diagonal. And that this is the same value that is the scalar, well, the reciprocal of that value is the scalar in the inverse formula. I'm also going to expect that we're able to do determinants by hand, or by hand for a 3x3, but no bigger than that. So, hi. Thanks, dude. Ava, it's the pass that you knew was coming.
Yes. Thank you.
You're welcome. Now, that's a heck of a looking formula, and I would not suggest trying to memorize this. We'll do an example here in a moment, and I'll show you the kind of a visual way of remembering how to do this. That's, I think, massively easier than trying to memorize this formula, which just looks like an alphabet soup of confusion to me. But the visual way I'll show you guys is pretty easy to remember what to do. And that's what we'll do next, is just do some examples of these sorts of problems now. Okay? So this basically summarized the last couple of lessons. So we have all the matrix operations and kind of the important facts about them all in one place here. And we'll just do a couple of examples of some of these operations. Coolio? Allie?
Could you do like a 2x3? Is that for a determinant?
So it must be a square matrix. So it has to be 2 by 2 or 3 by 3. It can't be something else. Yep. So let's look at some examples. Okay, so this is a matrix multiplication problem, and this is one that you should be able to do in your head. Good. How'd you know it was undefined, Luke?
Because the dimensions,
Mm-hmm.
the numbers.
Okay, so what's the dimension of this first matrix?
2 by 3.
Good. And the second matrix is a
2 by 3.
by 2. And those are the dimensions that need to be the same. And they're not. So there's nothing to do here. You just write undefined and you move on. Okay with that? Important for all these matrices that we check to make sure the problem is even possible before we start trying to do things. Because math teachers are a bunch of sneaky jerks and we love to give you problems that you can't actually do. Now, if we switch the order here, this would become something that's possible. So let's do that here real quick. So again, the first thing we want to do is check to make sure that they are indeed equal. And we know what the shape of the answer is going to be. It's going to be a 2 by 3, where it's the first component of the dimension from the first matrix and the second component of the dimension from the second matrix. So I like to draw out like a space for the different parts of my answer, so I have some place to put all my work. Oops, what am I doing? Okay. So for the first spot, I'm going to multiply the first row with the first column. And then I'll continue kind of following that same pattern. So first row with second column. And then first row with the last column. And now second row with the first column. Second row with the first column. Or sorry, second row with the second column. And then second row with the third column. So 10 plus 1 is 11. 5 minus 3 is 2. 0 minus 4 is negative 4. 0 minus 2 is negative 2. 0 plus 3 or 6 is 6. And 0 plus 8 is 8. Okay with that? Okay. So here we're looking for the inverse for this matrix. Before we start trying to compute that inverse, what do I have to check? Okay, I have to check to see if it's possible. So what do I need to look at to determine if this is possible? Okay, so what are the dimensions for this one? 2 by 2, so that's okay, right? That's square. Is there anything else? I also have to check its determinant. The determinant of this matrix needs to be non-zero in order for me to do it. Since this determinant was zero, there is no inverse for it. It is undefined. Everybody okay with that? Edmund?
I'm curious, how did you get that?
Okay. So for a 2 by 2 determinant, I take that diagonal and subtract it from that diagonal, or subtract that diagonal.
That's just an example of the like
This is just a problem. Yep. Isn't related to, oh, the previous problem? No, not in any way. Yep. Okay. Oh. I changed that. Okay. How about this one? Okay, we can do this one, right? It's 2 by 2, so that part's good. And its determinant is -2. So everybody good with that? So to do this, I'm going to be using my formula as for this matrix. Its inverse is 1 over the determinant times this kind of rearranged version of the original. So I have 1 over the determinant. And then I notice that for my main diagonal, oh my goodness, come on, switch locations. So for mine, those should switch locations. So I should have 2 first and 5 last. Everybody okay there? And then for my other diagonal, they stay in the same place, but the signs get flipped. So instead of 1, I'll have -1. And instead of -8, I'd have +8. Everybody's okay with that? Sergio? Yes, thank you. Okay. And the last thing I need to do is just do that scalar multiplication. So -1/2 times -2 is +1. -1/2 times -1 is +1/2. -1/2 times 8 is -4. And -1/2 times 5 is -5/2. So that's my answer. Amy?
You want us to put it back
I mean, if the decimal's terminating, it's okay to write it as a decimal, but if it doesn't terminate, I prefer the fraction. Mackenzie.
Could you do it for like other dimensions, like if it was like 2 by 3?
So must be a square matrix. That's the first thing we check is to the dimension. There is no inverse for a non-square matrix. Okay? All right. And last thing we'll do is do a 3 by 3 determinant here. We've done a bunch of 2 by 2s here in the previous exam, inside of the previous one, so I don't think we need to do another one of those. But I promised you there was an easier way of thinking about this than the awful looking formula that we wrote down a moment ago. So let's do that. So I know that this is a determinant problem. How do I know this? Because instead of drawing brackets, we have these vertical bars around it. So that's an indication that tells me take the determinant of this. So this is I'm going to just start by copying down the first 2 columns here on the right-hand side of my matrix. So just like this. And I'm just doing this so that it makes the formula easy to generate. Now I'm going to take the 3 diagonals like this, and I'm going to multiply those numbers together and add them up. Everybody okay there? Then I'm going to start at the bottom left-hand corner and take these 3 diagonals, multiply those things together, and then subtract them. And that's it. Does that seem a heck of a lot easier than that formula we tried to write down a moment ago? Pretty easy to remember that process in comparison to trying to remember the formula that we had a moment ago. So all we have to do now is to compute this. So I have 0 plus 0 plus 4. No, let's write them all down. Then I have minus a negative 4 minus a negative 18, and then minus 0. So I have what? 26. And that's it. What do you guys think? I argue that remembering this diagonalization method is much easier than trying to memorize that formula. This is easy to remember because it's just kind of a picture. And it's a pretty easy to remember picture. Mackenzie?
These also have to be square matrices.
Correct. Yes. These also must be square matrices. Correct. You guys feel okay? Okay. I'm going to stop the recording then.